course. Hello everyone. So I'm going to present a project I've been working on the last month because I have time thanks to Serge. So the content of this talk, I'm going to just say a bit of who am I, what's a function for interface, how we can do that with for C with Clang and LLVM, a small demo if we have the time about what's next. So my name is Adrian. I'm working on Corsa with the two previous guys, and we're watching LLVM-based obfuscator as you have seen. So about the subject, what's an FFI? So the Wikipedia definition is pretty straightforward. It says it all. It says it's a mechanism by which a program written in one language can call routines in another language. So in our cases, we want to be able to call C functions and maybe compile them from any language. So for instance, if we are in Python, we would like to say, okay, there's this putS definition, and I just want to declare my function and close it, and the magic happens, and everything works. So what's the big deal? Why is it hard to do that? When we want to call C functions from a higher level language, it's because we usually want performances, but C functions are compiled for a specific ABI, application binary interface. There is just one ABI, it's not standard, there's one ABI per system, per architecture, per whatever you want. It's kind of a mess if you try really to understand every ABI, you just don't want to do it, so you don't want to do it, so you want someone or a library to do it for you, and that's what you try to do. So there's a reference library which is really works well, which is called LLVM. It implements a lot of various ABI, and there's a C API to use it. So for instance here it's the ABI to code the hello world on putS, so it's pretty straightforward. And there's CFFI, which is a Python library, which uses LLVM to do that from Python, and it uses PC parser to parse definitions. So why we want to do another one if this library exists? So there are some issues. For instance, for LLVM, it's not that trivial to insert a new ABI. You have to do end return assembly. You've got to understand the whole ABI. So for instance, on our Linux, the MS ABI does not exist. And for CFFI, PC parser can parse anything. For instance, you want to include the file, it just doesn't work. If you have some custom attributes on a function, it doesn't work anymore. And I want to be able to use my library headers out of the box. I don't want to modify them. I want to maintain two versions of them. I just want to use them and it works. So that's why we started to try to do that using Clang and LLVM. So what's nice with Clang for that, Clang can parse C code. It's a good C parser. You won't have issues with attributes and stuff like that. Clang has support for lots of ABI, so you don't have to do it yourself. And LLVM can compile the whole thing, so it puts everything together and it works, right? But it's not that easy. One thing we need to do is to find the right type abstraction. Because we will parse C functions, we need to get these types and to work with them. So for instance, if we take the Clang AST, if we got a structure here, we see that the Clang AST will just give us the name of the and the type of the fields, but we don't have anything about the padding, about the layout, the final layout, and we need them to do our bindings. If we do that at the LLVM level, it's a bit too low level because it's LLVM. And for instance, in 64 bytes on Intel, we won't have any, on this code, we won't have any structure at all because of structure collapsing, I don't know how to say in English. Yeah, thanks. And so basically here the structure is passed by only a register and it just doesn't exist in the IR, so it's too low level. If you want us to see how it can change, if we just switch to 32 bytes on Intel, here the structure is here because the ABI is different, so you got a different code. And in this case, it can work, but it's not universal. So one way which is nice to have is to use dwarf debug information. It happens to be the right level we want. If we take this code and we compile with debug information, we see it tells us there's a structure, there's the name, the number, there's the type, and there's the size and the offset here. So the structure, the layout, which is specific to the ABI, is included in these informations. So what we did is that we take this dwarf metadata, we transfer them into our own custom types. Why we did that is because we wanted our library to be free from LLVM headers, so you don't need to use the LLVM headers to compile to use the library. And there's other things that we want also to have our type cross qualified. We don't need all the stuff from dwarf, so we need something in between. And to call a C function, we got this issue still. We need to generate the glue code, which call function from any kind of environment. So what we do is a kind of hack, but it works. We generate this wrapper for every function types. The wrapper takes a function pointer, and it takes a pointer to the return value and a pointer to a list of pointers. and then you cast it all in this wrapper, and Clang generates the IR, which is okay for the library. You don't have to do it, and everything works like that. Some issues we have reclaimed. The main one is that if you have unused declaration in your code, so for instance here we've got print A, and this structure is used by nothing else. If you compile this to LLVM IR, even with some flag which is called init all decks, it won't init all declarations. So you need to have some acts to force the stuff to be used, and it's not really nice to see. So one small demo. So here it's using a Python. 5 minutes left. It's using a Python bindings. So here, for instance, I've got the function foo. It compiles it using the jitter and codes it with 4 and 5, and 4 plus 5 is 9. Here I can include stdlib and use h2f from this library, and everything goes as it seems. Here I've got this structure point with 2 integers and 2 functions. So this function getCurrent, I call it, it will create me an object I can use directly from Python, and I can go through the numbers, and it goes as it should go. I can have memory views on this object, so here it's 2 integers in little engine in memory, so this 1 and 4. I can modify this one and reprint it, and it will give me 8 because the memory is directly modified. I can create a new point and use this multiplied by 2 function, and then I get the good point. And if I go a bit forward, here it's an example using OpenGR and RedGR from the libc. So I include GR-ents, I've got all my functions and structures I need. I can call OpenGR like we wrote in C in the end, try if the pointer is okay and everything. I just want this, for instance, and we make an implementation of ls, which is very simple. This one is a bit more complex. It's for libarchive. Libarchive is a C library, which is used for every, we support a lot of archive formats, and here it's really a mapping of the example you have in the libraries, the documentation to Python. I just write it the same way, and I'll have the extraction of that3, anyway, the term server. So, so what's next? If you look at the binary generated for Python, it's 55 megabytes, it's a bit huge. We've got a lot of things we can try removing the symbols, trying to do this with ITO and stuff like that. Try to force Clang to emit tab definitions that are not used. Related to the talk one day, we can use EasyJIT to JIT the whole thing from Python to C. So for now, we're evaluating our type tree, and then we could say, okay, for this function, this is this code, this is JITed, it just do only the things he needs to do. It currently works on Linux. I should take time to make it work on OS X and Windows. Something that some people say on the internet is that we could parse the debug information within a shard libraries, and so it should work because our main entry point is the draft information, so maybe we even don't need the header file in some case. And it can also be a basis for eval in C++ for the people who have been there in San Jose last October. One guy from LLD showed how we could make eval in C++, and maybe it's a basis to do that. It was a light talk, by the way, if you want to show it. So that's it. That's all for me. If you have questions. Yeah.
So you can't always, there's things to remember, this has been something people have been obviously trying to do and screwing up in various different ways for 30 or 40 years. If you have an argument which is a const char star, for example, you've no idea whether that's, it's a char star, you don't know whether it's a const, you don't know whether it's an input parameter or an output parameter. There's all sorts of complications. You get a struct passed in both. Yeah. Was that? So I doubt your DLL information has enough for you to tell whether things are constant or not.
But the dwarf information has.
Yeah, I should think the dwarf will be, if the compiler is good enough to put everything in there that you want to, and the programmer was good enough to mark things.
Yeah, sure. So two things. We need the const qualified thing because in Python, for instance, strings are immutable. So if you're in your API, you've got a const char star. You can say, okay, if my buffer view is read-only, and I've got a const in parameter, I can make this mapping because I've got the right to. If in C I've got a char star, I can do it. And it works actually. That's why I've got, because Clang generates the good things. So in Clang I've got the whole information. And actually if you take this, I don't have an example here, but in the test suite, there's an example of stuff like that. It really works because Clang does the good thing. And yeah. Time's up. Sorry. If you have questions, we can.